Hello, everyone, and welcome back. In this brief video, we're going to continue our discussion from the previous few videos, where we've been looking at how we can apply the definite integral to understand real-world problems and to solve problems that are primarily arising in physics using what we've defined and what we've understood to be work. Now, in this video, we're going to continue that exploration by turning our focus to fluids and trying to understand the pressures that they exert on, say, walls of containers that hold those fluids. So let's go ahead and jump right in. The first thing that I want to start with is emphasizing to you that when we build a dam to hold water, so if this is going to be my dam right here, and it's holding back some water, then the pressure that's being exerted on this thing varies with the depth of the water. And what you can see from my little picture here is actually characteristic of something we do in real life. When we build a dam, we have to make the bottom of it thicker. And this comes from the fact of what I just said, that the pressure that's exerted on this dam by this standing water that it's holding becomes stronger the further down you go. And we can actually characterize this perfectly. So if we say this depth here is, say, H, there is a formula that gives us the pressure that's going to be exerted on this dam. And this formula is very, very simple. It's linear in the depth. And it says that the pressure is equal to 62.4 H. Think about how interesting that is, right? This doesn't take into effect maybe how long the dam is or the volume, which would naturally give us the sort of volume of water that's holding. The only thing that matters here is the depth, and it comes up linearly. So we just multiply it by this sort of seemingly random number, 62.4. And in this case, this 62.4 is what's called the weight density of fresh water. And in this case, it's going to be measured by pounds per cubic foot. So we're using those imperial or those British units. And the 62.4 is the unique part to fresh water. But the really interesting thing is this equation is not unique to water. It's actually a characteristic of all fluids. And this comes through what is called the pressure depth equation. So let me give it to you in a little bit of generality here. So we're going to assume we have a fluid that is standing still. So in a fluid that is standing still, the pressure P at depth H is the fluid's weight density that's W. In the case of fresh water, this was the 62.4 times H. Written in symbols, pressure is equal to W times H. And you can calculate this out for all kinds of different fluids. We know what the weight density of most fluids or the fluids of characteristic interest to us are. You can look up tables of these things. Just in case you're wondering, say gasoline, this W would be 42. Something very thick like mercury, that's 84.9. Olive oil, like from the previous example, that was 57. Which was a number that we actually saw show up in the previous example. But the really interesting consequence of this thing is what it means for containers of different sizes. So for example, let me give us two different containers. Let's think about a nice cylindrical container. And let's also think about a container with a sort of like a skinnier top, but it has the same size of base. And so we want to ask ourselves, what is the pressure or the total force being exerted on the bottom of these containers? So imagine I fill them up with the same liquid, and I want to know which one of these is going to have a greater force that's being exerted on the bottom. Okay, so not on the walls anywhere, on the bottom of this thing. How much are we pushing on the bottom? Well, if we look at some of the units here, we get that pressure is per unit area. And so what we can find is a very, very simple formula. So the force, pardon me, maybe I'll put this in black so it stands out a little bit more. The force that's being exerted here, so this will be the total force. This is actually equal to the force per unit area times area, right? That's a relatively trivial thing. We just sort of divide and multiply by area. But what is the force per unit area? That's just the pressure, right? So if you don't believe me, go back to the olive oil example from the previous video. That's exactly what we did. So this is the pressure times the area, which from our previous formula is going to be WH, that's the pressure, and then times the area. But what does this simple little equation tell us? It tells us that as long as the same liquid is in both of these containers, and these things are the same height, so we'll say H, it doesn't matter that they're different shaped and that they have different volumes. The pressure, or sorry, the force being exerted on the bottom of these things is exactly the same, assuming they're filled right to the brim, right? That's the important piece, because H is measuring the depth. That's fascinating, right? Because I think there's an intuition here, at least for me, maybe someone who's not as physics-minded as I maybe should be, to say that, well, maybe the left container has more of a volume, so there's got to be some more weight crushing down. It has to be, to me, it just seems obvious that the left-hand object has a greater force being applied to the bottom of this. But this is really what's sort of unintuitive and really, really cool about this formula. Okay, let's see it in action. Let's actually do an example to drive this home. So let's imagine the following. So the example here is going to be, we imagine a flat isosceles right triangle plate, or right triangular plate, with base 6 feet, and height 3 feet, is submerged vertically and base up 2 feet below the surface, of a swimming pool. So we're assuming this is going to be freshwater again. So our W is going to be 62.4 again. So find the force exerted by the water on the plate. Okay, so again, imagine you've got a big swimming pool, maybe in your backyard or something like that, and you take this right angle isosceles triangle. It's got base 6 feet, and it's got height 3 feet. You submerge this thing in the pool vertically, right? So it sort of sets up a wall in the middle of the pool. Now the question is, what is the force exerted by the water on this plate? So now this isn't as simple as just applying that formula, right? Because the triangle is ranging over a different range of depths, right? So h is changing depending on where you are on the triangle. So what we're going to do is we're, of course, going to turn this somehow into a Riemann sum that eventually gives us a definite integral. But the idea here, very loosely, is to sort of subdivide the triangle by the depths and figure out what the force is exerted at each one of those depths, and then add them all up. And that will give us this Riemann sum to give us this proper definite integral. Okay, the first thing that we should do, of course, is set up a sketch. We're going to need some formulas for equations here. So this is where we need to start. Let's imagine we've got ourselves on the XY axis here. And we have a triangle. We are 2 feet below the surface of this thing. So I'll use blue to denote the surface of the water. So let's say the surface is at y equal to 5. So that means that the triangle goes up to y equal to 3. So the peak of the triangle, or the sort of right angle, is at 0, 0. We go up to y equal to 3 here. This is an isosceles triangle. So this is 3 units. Its base is 6 units. So we're going to go 3 to the right and 3 to the left. So let's imagine we've got this point right here and this point right here. And so we've moved 3 units backwards in X, and we've moved 3 units forward in X. And let's set this up. That's my isosceles triangle that's underneath the water here. And so then the question is, what is the formula of each one of these lines? So we can see that this goes through 0, 0 and 3, 3. This is a very, very simple formula. This is y is equal to x. Similarly, this line is given by y is equal to minus x. Okay. And so now the question is, how do we set this thing up? How do we turn this into a Riemann sum? Well, we can see that the depth here is coming down from y equal to 5. And so that means that we're using this vertical component to measure the depths. That means that our h should be in terms of y, okay? And what we're going to do then is we're going to subdivide this triangle into thin little slices. So just like what we've done in all the previous problems. So we're going to skip some of the steps. We're not going to write it out as we do in all the detail usually. But let's imagine, let's create a slab between, say, y and y plus delta y. So between y and y plus delta y, we have a slab. We're going to assume that delta y is so small, maybe I should draw this, that just assuming this thing is a rectangle will be good enough. Oh, sorry. Just assuming this thing is a rectangle is good enough for us to get away with this, because delta y is going to be so small. You know, the extra little angles here aren't going to make a difference. So we have a slab, and the pressure on this thing is going to be just that 62.4 multiplied by the depth or the height of this thing, the h variable. So we get P is equal to 62.4. And now the question is, what is the depth? Well, if we've moved up y units on the y-axis, then the distance that we have to y equal to 5 is 5 minus y, right? So if I draw this over here, maybe I'll put this in green just so we can see it. if I go up to some value y, this thing here is distance y. Maybe this is overkill. And then this distance here is 5 minus y. So that tells me the depth is 5 minus y. Okay, then what is the area of this slab? So the area of this slab is going to be, so area of slab. Again, we're assuming this thing is equal to a perfect rectangle. So then we have a height of delta y, right? Because we're going between y and y plus delta y. And so that means, what is the length of this slab? Well, in this case, the length of this slab is going to be the distance. Maybe I don't want to make my drawing too ugly, so I'll just put one more thing on here. I'm going to call this L of y. This is the distance across this slab, and we're actually going to be assuming it's coming from the bottom. It won't matter in the Riemann sum anyways, but we're going to get length times height, which we'll say is L of y times delta y. And so the question is, what is L of y? Well, L of y is the distance from the function x equal to y to x equal to minus y. So the same x value, different, or in this case, you're stretching from one piece of this to the other piece of this. You can break this up in a simple manner, and you can ask yourself, what is the distance from the y-axis to this curve, and the distance from the y-axis to this curve? And you can see that each one of those distances is given by y. You're moving x units, and x is equal to y on that thing. So it's the same thing that we did with the olive oil example, right? So that means that the length of this thing is 2y, and therefore the area of it is 2y delta y. So then this tells us that the force being exerted on this, the force of each slab, actually, I don't need to put in is, this thing is equal to the pressure and then multiplied by the area, right? The pressure is force per unit area, and therefore we multiply the area to get the full force. And so that gives us 62.4 times 5 minus y times 2y times delta y. So I won't simplify it just yet. And what I'm going to do here is I'm going to skip some steps, right? Because we've done this a lot. We've seen how this works. We're basically going to put this into a Riemann sum, let delta y go to 0. And that is the same as saying the number of partitions goes to infinity. And so that means that after using this Riemann sum, after doing the full convergence argument that we always do, this tells us that the total force, F, is going to be a definite integral. And this is going to be a definite integral of the force of each of these sort of slabs as delta y goes to 0. So 5 minus y, 2y, dy. And now we ask ourselves, what are the bounds on the integration here? Well, we can see that we go all the way down to y equal to 0 at the peak, or sorry, at the apex, I suppose, of this triangle. And then we go all the way up to y equal to 3, which is right here. So this is y equal to 3. So our bounds on integration here are 0 to 3. And now life is good, right? We're right back into a math problem where all we have to do is calculate a definite integral. And by this point, we should be very good at definite integrals because that's what we just keep doing, right? The hard part is getting there. Hopefully the easy part is just solving these things. So let's clean this up a little bit. Let's pull the 2 and the 62.4 outside. I get 124.8. The definite integral from 0 to 3. Maybe we can multiply that y in as well. So I get 5y minus y squared dy. Now I've got a nice quadratic function to integrate. Let's just go ahead and find the antiderivative. This gives me 5 over 2y squared minus y cubed over 3, running from 0 to 3. Calculator problem, right? We're probably sick of hearing me say that, but what I want to emphasize by saying that is that, you know, all you need to do is get to the definite integral, and now you're at the easy part, hopefully. And so you can simplify this thing out. You get 160 or 1684.8 pounds of force that's being exerted on this thing. So just to summarize what's happening here, you know, you're doing the same process. You're creating a Riemann sum. You take the limit as delta y goes to 0, which is the same as letting the number of partitions go to infinity. You sort of subdivide these into little slabs with each one of them as height delta y. So if you can figure out the difficult part of how to set up the Riemann sum, then you can certainly solve the problem, I suspect, because beyond the Riemann sum, then you just move to a definite integral, and, you know, boom, boom, boom. Now we got an answer. So hopefully we've seen in the past few examples, you know, how these Riemann sums can be used to build up the definite integrals and answer actually interesting problems that people in the real world might actually have.